In the last part, we have seen a stress field around a screw dislocation. In this part, we'll be looking at stress field around an H dislocation. So for doing that, let's consider a cylinder and which has been sheared along this direction. So let's mark the coordinate axis as x, y, and z in this way. And here, the axis of the cylinder lies around z-axis. And also a dislocation line which lies along a z-axis. Let me mark that. So we have a line, dislocation line vector t along z direction, and d is in this direction which is perpendicular to t direction. So we have t vector perpendicular to Burgess vector, and this represents an H dislocation. So we have an H dislocation over here, and to find out a stress field around a dislocation, what we do is, I have mentioned you already that we will find out what is displacement, and then we will convert it into strains, and considering elastic relations we can find out stresses. Okay, this is what the strategy we follow for finding out stress fields around dislocation. So in this case you can see that there is a displacement along this plane. Let me mark that plane. So we have a shearing on this plane, and you get a displacement on this plane. So we have a dislocation line along this z-axis. Let us mark that. So we have this dislocation line, and this dislocation line is infinite. So we have infinite dislocation line, and which is along a z-axis. And let's mark the displacements here. So we have W to be equal to 0, which is a displacement along z-axis. So we have W to be 0, and U and V are non-zero. That is displacement along x-axis and displacement along y-axis to be non-zero. And this represent a condition of plane strain. So this is a kind of a plane strain problem. However, to figure it out, these displacements, we need a different type of elastic theory which we haven't covered in our course, or which is beyond our course. So whatever the displacement which we get, we are writing it directly, and thus the stress fields also, whatever we are trying to find out for an H dislocation, remains very complex, and thus we are here directly mentioning the stress fields rather than deriving it, because the stress fields are complex, and the type of theory, elastic theory, which is needed to explain this stress field is beyond scope of this course. So let's write down the answers for the stress field. So we have sigma xx, which is given as minus gb upon 2 pi 1 minus mu by 3x square plus y square upon x square plus y square whole square. Similarly, we can find out sigma yy, and sigma yy is equal to gb upon 2 pi 1 minus mu into y, x square minus y square upon x square plus y square whole square. And sigma zz, you can write it in terms of a Poisson ratio, like sigma zz equal to mu into sigma xx plus sigma yy. How we can write this? Because you have displacement W equal to 0 along z direction, so you have a strain, that is epsilon zz equal to 0. So you can write this relation, and sigma zz can be given as gb mu upon 2 pi 1 minus mu y 1 upon x square plus y square. And you have shear stresses, that is tau xy tau yx equal to gb upon 2 pi 1 minus mu x into x square minus y square upon x square plus y square whole square. And other shear stresses such as tau xz and tau yz are 0. So we have these 4 shear stresses to be equal to 0. Now in this stress field, what you can observe is that you have normal stresses and you have also shear stresses. So in this, we will have the stress field around an H dislocation. We will have both. Let me write it down. So we will have both hydrostatic stress field and deviatory also. and this is for an H dislocation, and for screw dislocation you will not have heterostatic field around it, you will have only deviatoric. In case of H you have both. So we have both heterostatic and deviatoric stress field around an H dislocation, and we'll see the implications of this when we see these dislocations are interacting with other defects or other dislocations in the crystal. Now let's look at this stress field around an H dislocation. So we have these relations, that is the stress field, that is sigma xx, sigma yy, sigma zz, tau xy, which we have figured it out for an H dislocation. So let's see how this variation of sigma xx, sigma yy, and tau xy around a dislocation. So for that, let's mark the axis, coordinate axis as x and y, and let's put a dislocation, an H dislocation, positive H dislocation at the center of this, or at the origin here. And now you can say that, or just mark these two lines which are x equal to y and x equal to minus y, and let's put these elements in all these quadrants. And here let's consider this equation, like sigma xx equal to minus gp upon 2 pi 1 minus v y 3x square plus y square upon x square plus y square whole square. So this is the relation, this is an equation to find out what is sigma xx. Now if you look at this equation closely, you can see that when y is negative, sigma xx turns out to be tensile or positive, and when y is positive, sigma xx turns out to be negative, because you have this negative sign here, and whether x is positive or negative, it doesn't have any effect on sigma xx. Only the y value will have effect on sigma xx. So if y is positive, sigma xx is negative, that is, it is compressive in nature. When y is negative, sigma xx is positive, and it is tensile in nature. So let's do that. Let's mark here for y to be negative. Let's mark on this elements sigma xx. So has sigma xx to be tensile in nature, for y to be negative. Similarly, for y to be positive, you have sigma xx to be in a negative. So sigma xx is negative, and sigma xx negative means it is in the compressive nature. So let's mark on these four elements when y is positive that sigma xx is compressive in nature. So we have marked sigma xx to be in compressive nature. Now sigma yy, so you can see here the two terms which determines the nature of sigma yy is y itself and this term x square minus y square. So for positive y and x greater than y, you can say that sigma yy is positive. For before that, let's mark what are on this axis. Okay, so on this axis you can say that y is to be 0, and thus for y equal to 0 you have sigma xx to be 0, sigma yy to be 0, and sigma xx and sigma yy is 0. That means sigma zz is also 0. So on this axis, sigma xx equal to sigma yy equal to sigma zz to be equal to 0. And you can write for y less than 0, sigma xx to be greater than 0, and y greater than 0, that means sigma xx is less than 0. That is, sigma xx is compressive and sigma xx is tensile here. So let me write it down that also. So here sigma xx is compressive, and here it is tensile in nature. Now let's mark sigma yy here. So you can have x greater than y, that means this term to be a positive, and when y is positive you have sigma yy to be tensile in nature. So we have marked this sigma yy to be tensile in this where x is greater than y and y is positive. Similarly, for this element you can find out x is greater than y, and for y positive you have sigma yy to be positive, that is tensile in nature. So let's do that. So we have marked sigma yy to be in tensile nature here. Now at these elements you can say that y is negative and x is greater than y, so that means y will be the determining factor for nature of sigma yy. So at these elements will have, at these locations will have sigma yy to be in compressive nature. So we have compressive sigma yy here on these two elements. Now let's look at these two elements. So here y is greater than x, and thus this term turns out to be negative, and the sigma yy will be compressive on these elements. So you have compressive sigma yy. Similarly, when y is negative and y is greater than x, so you have negative and negative, which turns out to be positive. So sigma yy will be tensile in nature at these locations. We have sigma yy to be tensile in nature. Sigma yy will be 0 when x equal to y. So when we have x equal to y, sigma yy will be 0. Similarly, tau xy, where we have this term x square minus y square. So on these lines, sigma yy and tau xy will be 0. Here also sigma yy equal to 0 and tau dash xy is also equal to 0. On this axis, that is y axis, where x is 0, so you have tau xy, which has this term x, so it turns out to be tau xy equal to 0 on this axis, which is y axis. Now let's look at shear stresses, that is tau xy. So when x is positive, that is x is positive here, and x is greater than y, that means tau xy will be positive. So we have defined tau xy to be positive. So how to mark that tau xy? If you go and look at the conventions, so we have mentioned that for tau, it should act on a positive phase and along positive direction. The tau should be positive. And for negative tau, what we have said, it should act on a positive phase along negative direction. This was a convention which we followed for marking tau. So you have tau xy to be positive here. So you have, this is an x plane perpendicular to x direction. So this is an x plane. So this tau, if I want to mark, I have to mark it in a positive phase. So this is a positive phase, positive x phase, and it is for along the positive y direction. So this tau becomes positive. Similarly, this tau, or the shear stress on y plane, it is acting on positive y plane along positive direction, positive x direction. That's why it is a positive shear stress. So we both shear stresses, that tau xy will be positive here. Now let's look at here. So here you can say that when x is less than y but x is positive, that means tau xy turns out to be negative. So negative shear strain, how we'll mark, that is on a positive phase along a negative direction. So this is what the convention is. So we have marked this shear stress in this way, and this is also, see the shears, this shear stress also is acting on a positive phase but in the negative direction. So this is a negative shear stress. So we have marked these shear stresses. Now let's look at this location where you have x to be greater than y but x is in a negative direction. So this shear stress will be negative here. So we have marked these shear stresses on this element. And if you look at this position where x is negative but x is y is greater than x, so this becomes negative and negative and it becomes a positive shear stress. So we have positive shear stress at this location, so we have marked the positive shear stresses on this element. And similarly, you can mark the shear stresses on every other elements here. So we have marked what are the nature of sigma x, sigma y, sigma z, sorry, not sigma z, sigma xx, sigma y, and tau xy, where sigma z is along this direction, which is perpendicular to the screen. Now let's look at this stress field around an H dislocation. So we have these relations, and we have said that sigma xx is compressive when at this quadrants, and sigma sigma xx is positive, that is tensile in nature, below the slip plane. So let us write it down. So when we have a dislocation here, so we have a compressive stress here, which is this is half plane, and below half plane we have tensile stress. This is what is being represented over here. So we have a compressive stress field where there is an extra half plane, and below extra half plane we have tensile stress. Now if you see the variation of sigma yy with x and y, you can say that this is, you have sigma yy to be compressive in this region where y is greater than x and y is positive. When y is negative, this will be a tensile nature, but for y greater than x. So let me write it down. So here this is a region where y is greater than x, and this is a region y is greater than x, but here y is positive and here y is negative. So in this region you have sigma yy to be tensile in nature, while this region you have sigma yy to be a compressive in nature. Now when you see these regions where x is, let me write it down. So when x is greater than y but y is positive, you can say that this sigma yy turns out to be in a tensile nature. So you can find out from these relations. Similarly, you can find out at this location sigma yy turns out to be a compressive in nature. Now if we want to find out tau xy, how is the stress field around at this location, so you can find out that for this region, let me write it down, for x greater than y and x is positive, you can say that you have tau xy or sigma xy to be tensile in nature, while for this region where x is greater than y but x is negative, you can say that this is a compressive in nature. Let us write it down. X greater than y but x is negative. So you have this region, and there are this region where y is positive and y is greater than x. So you can say that, or x is positive here and y is greater than x, you can say this is a compressive nature of tau xy. So we can find out these plots from all these relations. Now what I want you to do is that let's consider an H dislocation when I consider this coordinate axis at the origin here, and let's consider another H dislocation of same type. So let's say these are two positive H dislocation, but it's on another slip plane and having, let's say, Burgess vector B, and this also having a Burgess vector B. So these are two dislocations of same sign having Burgess vector B. What I want you to find out that this Klein force on this dislocation 2 because of stress field around dislocation 1 will be minus sigma xx into B. So you have a compressive stress over here, and let's say this compressive stress will act on the extra half plane, which is normal stress to this. So what will be the climb force? It will be minus sigma xx into b. Similarly, you can find out a glide force, that is tau yx into b. So you have shear stress acting on this glide plane, which is marked here, and let's consider that as to be tau yx, and the glide force can be written as tau yx into b. This we have seen to find how to find out glide force and climb force using general considerations of stresses, also using Peach-Kohler equations. Now what I want you to find out, what is the stress field or the variation of stresses, this glide and climb forces, when I move this dislocation along on this slick plane. So how does the glide force vary with respect to x? That is what I want you to find out. We'll be looking at this condition in future, but in meantime you can find out how does this glide force vary with x. And with this I will stop here.